Over the last 2 days, we've started looking at how to add vectors together that are not in one dimension. Back in the day, 10 years ago, we thought 3 plus 4 was always equal to 7. A couple years later, we learned 3 plus 4 could be minus 1 if the 4 was in the opposite direction. It could be plus 1, okay, if the 3 was in the opposite direction. So in other words, we learned to add vectors together. But we learned to add them together in one dimension. 2 days ago, we learned to add them together when they're in 2 dimensions. In order to add 2 vectors in 2 dimensions together, we have to draw what's called a vector diagram. There's certain rules for drawing that vector diagram. The first rule is make sure that your vectors, remember what a vector is. Okay, it's a vector, it's a line segment with an arrow on the end of it. Make sure those 2 vectors, when you're adding them together, are drawn which way? Which way do you got to draw? How's this? Does that work? Why not? Because they're back to back. Okay? This one doesn't work either because they're drawn front to front. So we can't do those. If we want to add those 2 vectors together, we've got 2 options. Both of those options have to involve them being drawn front to back or front to back. Now, the resultant vector, that vector that joins together the start to the finish, the one that's drawn back to front, the one that's drawn backwards, basically. The resultant vector is the sum of those vectors. Just like 7 used to be for us always the sum of 3 plus 4, that green vector that you see up on the board is the sum of whatever those 2 vectors are. Now we can find that green vector quite easily using some grade 8 or grade 9 math. Let's call it R here. How do I find the value of R? Assuming that I'm given the value of both of these variables. Okay, let's say I know what that number is and I know what that number is. How do I find R? Yep, R. The Pythagorean Theorem, right? A squared plus B squared is equal to C squared. The form of it that it takes for us looks more like this. R is equal to the square root of A squared plus B squared. But it's exactly the same thing, right? Okay? A squared plus B squared equals C squared. We're essentially just calling C R for the resultant vector. Okay, if you want to call it C, go ahead, I guess, and call it C. It's not really a big deal. Now, there is one more thing that we need, though. The resultant vector, the sum of the vectors, is a vector. So in addition to magnitude, we also need what? Magnitude and direction. The direction is going to be indicated here by an angle. How are we going to find that angle? Okay. Yeah, sine, cos, and tan. Now, sine and cos, they're technically okay here because at this point you would have all 3 sides, the opposite, adjacent, and hypotenuse. So technically you could use any of the trig functions. The one that I would suggest you use is tan because tan uses opposite and adjacent, and those are the 2 sides that we were given. So if we use tan function, even if we made a mistake with the Pythagorean theorem, we're still going to get the angle correct. Does that make sense? So my recommendation would be to use the tan function or the inverse tan function of opposite over adjacent. We'll call it, in this case, y over x, the up one over the horizontal one. Good? Now in your calculator, of course, you're just simply going to enter second function, tan, and then enter the 2 numbers for those 2 variables, those 2 axes in brackets, and then press enter. Yesterday, we went a little bit further with this. Yesterday, we said, well, what do we do if we have 3 or 4 or 14 vectors that we have to add together? Because we can't just draw those and get a triangle. For instance, I've got 3 meters. I've got 6 meters. And I've got 1 meter. I can draw a vector diagram with that. I mean, there's no problem with that. Let's start down here. Here's a good vector diagram. That's 3 meters. That's 6 meters. And that's 1 meter. It's okay to do that and draw the resultant vector from start to finish. But it doesn't help us directly in solving for the resultant vector because it's not a triangle. So what we have to do is get a triangle out of it, a right angle triangle out of it. How do we do that? Let's break them up into x's and y's. Call this one number 1, 2, and 3. What's the x component, please, of vector 1? X component, remember, is horizontal. Y component is vertical. How much of that 3 meters is horizontal? All of it, right? So we're going to say it's 3. How much of this one is horizontal? None. 0. And how much of this one is horizontal? Be careful with this one. What is it? -1. Good. Negative because it's going in the opposite direction to the left. So we're going to say that the total x here ends up being equal to 2. Now let's look at the y component. The y component, the up and down component of that 3 meters is, there's no easier answer than answering this question. 0, nothing. There is nothing. The answer is nothing. The y component of the 6 meters is 6. And the y component of the 1 is 0. We add those up and we get 6. So that was pretty easy addition there. Well, now we can draw a right angle triangle. We've got 2 to the right, and we've got 6 up. We draw a resultant vector like this. If you go back to that original diagram I drew, the one that wasn't very helpful to me, this one right here, wasn't very helpful because it wasn't a triangle. You can see that the resultant vector still looks pretty much the same as it did in my second diagram. If I had drawn it to a perfect scale, the resultant would have looked exactly the same. It's just that the second diagram is easier to find the value of it because now we have a right angle triangle. Now let's just go back to what it was before, right? A squared plus b squared is equal to c squared. Theta is the inverse tan of opposite 6 over adjacent 2. Get your angle. Good? This is question number 1 that you had to work on for homework last night. We have to add these vectors together. Now, we can draw a vector diagram with all 5 of these vectors. We can do it fairly easily. 20 meters to the north. Let's start over here a little bit so we get some more space. We have 20 meters to the north. We have 30 meters to the west. We have 25 to the south. We have 30 to the east. And we have 10 to the east. The resultant vector would be drawn right there. Great. That's a good vector diagram. But it doesn't allow us to find the resultant vector. It doesn't allow us to get the sum of those vectors. Right, Kirk? Sorry, you're right. Yeah, you're right. Yeah, good point. Sorry. It always goes from start to finish, right? Absolutely. Okay, from the tail or the back of the first vector to the front of the last vector. Right? Again, it's still not very helpful to me right now, but we can change this into a form that is helpful to me. So let's do that. Let's do our x's and y's. 20 meters north, how much of that is x? How much of 20 meters north is this way? None. How much of 30 meters west is this way? Negative 30. Negative, why, Rickard, why is it negative? Yeah, you're going in the opposite direction. Okay? 25 meters south would be 0. 30 meters east would be positive 30. 10 meters east would be positive 10. We add these up, we get a value of positive 10. The y components, well, this is going to be 20, 0, negative 25, 0, and 0. Add those up, we get negative 5. Now the question is easy. Now we just redraw it. 10 meters, 5 meters, and the resultant vector goes from start to finish, or from the back to the front. What does that equal? Square root of 125 would be just over 12. To 2 digits, it would be 12, right? Theta is equal to the inverse tan function of 5 over 10. The inverse tan of 0.5. Going to give me, what, about 30 degrees? 35? 34? Good? How many people got that? All right. Today, we're going to go one step further with this. Today, we're going to go and deal with funny angles. And by a funny angle, I mean something that's not 90 degrees. In other words, what if I'm trying to add this vector to this vector? How do I do that? I can't just say, well, this one's 10 and this one's 5, and okay, x and y is in 10. We don't know what the x is and what the y is, right? Both of them have partly x and partly y, right? It's not going 10 over in the x direction. It's not going 10 up in the y direction. It's going 10 over and up. How much of that 10 is over and how much of that 10 is up? Once we figure that out, then we can treat it just like we did the last sets of problems that we've done over the last couple of days. So how do we do that? Well, let's start off by just recognizing the x and y components once again of straight, horizontal, and vertical vectors. What's the x component of this? How much of this is x? What's the x component of the 10 meters? Bailey? 10 meters. Good. All of it is. How much is y component? 0. How much is x component for this one? Wayne? 0. Good. Thank you. How much is y component? Wayne? 200. Good. How much is x component for this one? 50? Or minus 50. Good. Thank you. How much is y component? Good. How much is x component for the last one? Aiden? 0. How much is y component for the last one? Negative 35 because it's going downwards. Good? I think we're all okay with that, right? But what about these? How much of these are x and how much of these are y? Here's what we're going to do to determine that. We're going to turn these vectors into triangles. So I've got 100 meters we call that actually 30 degrees north of east. I'll explain what that means later on. Okay. Bottom line is we have an angle of 30 degrees from the x-axis. We're going to draw a triangle around this angle like this. We're going to label this x. We're going to label this one y. We're going to do the same thing over on this one. We're going to draw a triangle around the 30 degrees. We're going to label this one x and this one y. Now, how do we go about finding how much of that 100 is on the x-axis? Got an idea, Rucker? Yeah. Which side of the triangle, Rucker, is the x side? Opposite or adjacent? Good. So this is the opposite, this is the adjacent, this is the hypotenuse. I have the hypotenuse. I'm looking for the adjacent. Which trig function relates adjacent to hypotenuse? So, ka, toa. Adjacent hypotenuse is cosine. So let's say cosine 30 degrees is equal to x, that's the adjacent side of that triangle, divided by 100 meters. The answer is 86.6. How much of it is horizontal? How much of it is x component? Well, most of it is. Some of it's vertical, but most of it's horizontal. Let's find the y component by using the sine function. Sine is opposite over adjacent. Well, the opposite side is y divided by adjacent, hypotenuse is 100. Y is going to be equal to 50. How much of it is horizontal? 86.6. How much of it is vertical? 50. Once we have how much is horizontal and how much is vertical, then it turns right back into one of these problems. We've got, 86 to the east, and then we had 50 to the north. We can add those together with other vectors the same way as we did in that example that we did here a few minutes ago. Okay? Yeah. Yeah. So you can do the Pythagorean Theorem. Yes, you can, but I wouldn't recommend that. Although it's valid, I wouldn't recommend it. The reason I wouldn't recommend using the Pythagorean Theorem once you get x to get y, although you can, and I won't mark it wrong if you do it right. The problem is, if you made a mistake here, then this one is automatically going to be wrong if you do that. Does that make sense? Whereas if you go sine and cos, and you make a mistake right here, well, you can still get this one right. So basically, it takes us back to original data, as opposed to using a number that we calculated, as we would be with the Pythagorean Theorem there. We're using original data, which is always better than numbers that we've already calculated. Okay, let's do this one. How much of this one is x and how much is y? Which side of the triangle is x? Opposite adjacent hypotenuse. It's not the hypotenuse, right? That's 20. That's the long side. Fraser? Good, it's opposite. So if we're looking for opposite along with hypotenuse, we're not going to use cosine. This time we're going to use sine for x. Sine 30 degrees is equal to x over 20. X ends up being equal to 10 meters. How much of that 20 is to the right? 10. Let's find the y component. That's going to be cosine 30 degrees is equal to y over 20. Take the 20 out by multiplying. Y becomes equal to 17.32. So the y component, how much of the 20 is y, or downwards? 17.32. Technically, we'd make it a negative value, right? Because it's downwards. Right? That makes some sense? All right, I'm going to give you a couple of examples now that I want you not to add together, just to find the x and y components. How much of them are x and how much of them are y? First one is going to be easy. It's 100 meters straight down. This one is 100 meters at 30 degrees north of east. And finally, the third one is going to be 100 meters at 60 degrees west of north. Find the x and y components of all three of those, please. To do that, remember, draw the triangle around it if it's not just either horizontal or vertical right now. Find the x side, find the y side. Use whatever trig function you need to use. All right, let's take a look at the first one here. The x component of the first one is 0. There's no triangle to draw here. We only need to draw the triangle when we've got an angle that's not normal. It's not straight up or straight down or straight across. Essentially, you got an angle other than 0 or 90, you're going to use the triangle. When you got an angle that's 0 or 90, you don't use a triangle. The x component of this one is 0. The y component is negative 100. Negative because it's downwards. Okay? Easy enough, I think. Now this one's a little bit trickier. This one, because it does have that funny angle, we need to complete the triangle around the angle. Label this one X, label this one Y. The X component of this triangle is which side? Opposite, adjacent, or hypotenuse? Next to the angle, right next to the angle, adjacent to the angle is what, Travis? It's the adjacent side, right? X, or the adjacent side. So we're going to use cosine for that, since it's adjacent over hypotenuse. Cosine 30 degrees is equal to x over 100. X ends up being equal to 86.6. I think it's 80.66. Is it 86.6 or 86.7? Close enough. Now the y component is the opposite side to the angle. It's across from the angle. So it's going to be sine 30 degrees is equal to opposite over hypotenuse. And that's going to be 50 meters. Is that okay? Finally, the third one. We've got 100 meters again, but this one's at an angle of 60 degrees, not 30. Let's draw that triangle around the angle. Somebody might say, well, why don't we draw the triangle right here? Why don't we draw the triangle right there? Because the angle's not labeled right there. We want the angle to be inside that triangle, and it's not inside that green triangle. It's inside the blue one, so that's where we should draw. All right? This is X. This is Y. Which side of the triangle is the X side? Opposite which means we're going to use sine. Instead of cos for X, it's sine for X. Sine 60 degrees is equal to X over 100. X ends up being equal to 86.6. But this time it's actually a negative value because it's going to the left. Cosine 60 degrees, that's going to give me my my y side, my adjacent side. Hundred times cosine 60 is 50 meters. See, my numbers are exactly the same in the second one as in the third one. My sign's a little bit different, but my numbers are exactly the same. Look at the vectors. They're virtually identical vectors. Somebody might say, well, one's at 60 degrees, one's at 30 degrees. But if you went and actually figured out what this angle was right here, what would it be? It'd be 60. So it's almost the same problem, despite the fact that we had a 60-degree angle and a 30-degree angle. One was cos for X, one was sine for X. We ended up getting pretty much the same thing. Good? Yeah. Yeah, that's a good question. I didn't really pay attention to the figures there, to be honest. I should have. They both should be two significant figures because the angle is 30 degrees, right? So this one technically should be 87. This one should be 50. A lot of times when I'm doing this, I don't do sig figs because it's not usually the end of the problem. Usually it's part of a bigger problem, and you want to save decimal places until later on. But strictly speaking, for this question, it was the end, and it should have been round. Whoops. All right. Let's try one example here. We're going to add these vectors together. By the resultant vector. Easily draw the resultant vector from start to finish or from back to front. Is that okay, by the way? Is that vector diagram, the legitimate vector diagram? All the rules followed? Front to back, back to front. Yeah, it's okay. Okay, we can't solve anything the way it is, but it's drawn properly. we have to break this up into x and y components. But one of them is a little bit trickier to find the x and y components. Let's take that 20 meters here, vector number 2, draw it off to the side over here. Okay, draw the exact same vector off to the side over here. This is x, this is y. Let's get the x and y components of that vector, just like we have with those 3 examples that we just did. Cosine 30 degrees is equal to adjacent over hypotenuse sine 30 degrees is equal to opposite over hypotenuse. It's 10, but we're going to make it negative because it's going down. I'm going to draw a little line around it, just reminding me that this isn't really the problem that I just solved. This is just kind of an aside to help me solve the real problem. Now let's go x's and y's for each one of these. What's the x component of the first one? How much of that 10 meters is x? Now, the second one, this is the trickier one. How much of that second one is x? Yes, 17.32. You got to keep in mind, after we do this little aside here, after we get the x and y of that one vector, that 20 meters at 30 degrees no longer exists for us. We were never going to use that number again. 17.32 meters, because we just found the x component of the 20. Next one, the third one, 0. We add those up, 27.32. For the y components, we get 0. We've got the second one. Second one. Josh, will take you ready to raise your hand there. No, the y component of the second one. This one right here. How much of that 20 is down? It's negative 10. Good. We just found that, right? The x is right here. The y is right here. And the y component of the third one is 20. Adds up to give me positive 10. Now let's redraw it. Just like we did with the problems you had for homework. Right? The only difference between this problem and those 3 problems you had for homework is this stuff over here. This stuff over here is different because we had an angle that was not 90 degrees. We had a funny angle, an angle that we don't like. So we get rid of it by doing this stuff. Okay, otherwise it's exactly the same. 27.32 over. We get 10 meters up. Resultant vector goes like this. Went back to my original diagram. Resultant vector looks pretty much the same. Let's find what r is, and let's find what theta is. R is the square root of 27.32 squared. And theta is the inverse tan of 10 over 27.32. Let's do these on our calculator here. Okay, let's say square root, second function, x squared of 27.32 squared plus 100 squared equals 103, or 1.0 times 10 to the 2. To find the angle, it's going to be the inverse tan, or second function tan, of 10 divided by 27.32. we get 20 degrees. Yep. Oh, sorry. Yeah, you're right. That's going to change that, isn't it? I squared it already, right? I guess when I wrote down 100. So let's change that here. Let's say the square root of 27.32 squared plus 10 squared, square root that. Maybe a 29. That makes more sense. Thank you. 29 meters. It's pretty hard to have 27 meters one way, 10 meters another way, and end up with 100 when you combine them. But 29 makes a lot more sense. Is that okay? Yeah, we can. Yeah. You can see how, though, like, over the last couple of days, we've gone in steps here to lead us to this, right? We started off with add this vector and add this vector, right? And that was easy. It was a 90-degree angle already. There's a Pythagorean Theorem and the inverse tan function. And then we went to add this vector, this one, and this one. Well, that was easy enough. We had to break it up into x and y components, add up the x's, add up the y's, and then redraw it. Well, then we went to finding the x's and the y's for this one. And then finally we went to combining everything and saying, look, we know how to add these up. Let's get the x and the y for this one, and then just treat it like this problem. Okay, one more. And then I'll give you something to work on, and that'll be it for the day. All right, so we want to add these things together now. It's no harder than the last question. The resultant vector would be drawn right there. We've only got one funny angle. That's the 50 meters at 30 degrees. Let's redraw that off to the side here. Let's go right down here. Got some space here. At 50 meters, we got 30 degrees. This is x. This is y. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. X ends up being equal to 34.64. The y component, excuse me, the y component, we're going to say sine 30 degrees is equal to opposite over hypotenuse. Y ends up being equal to 25, but it's going to be negative because it's downward. That's our aside. That's what gets rid of this one right here. We no longer have that. At 50 meters at 30 degrees doesn't exist anymore. We've replaced it with 34 across and 25 down. This one is also negative, actually, by the way, isn't it? Because it's going left. They're both negative, left and down. Okay, let's do x's and y's. The x of the first one is 100. The x of the second one is 0. The x of the third one is negative 34.64. Add those up. We're going to end up with 65.36. Y components, 0, negative 50, and negative 25. These are easy to add up. Get negative 75 meters. Let's redraw it. We got 65.36 to the right. We got 75 down. And the resultant vector is drawn from back to front. Notice the resultant vector is the same as it was in my original diagram. Now it's just more useful to me. Let's get the value of r here. It goes square root of 65.36 squared plus 75 squared. We get 99. And finally, we're going to say the the inverse tan second function tan of 75 over 65.36. Make sure your calculator is in degree mode, by the way, guys. Degree mode, click mode. Make sure it says degree mode right there. We get an angle here of 49 degrees. Is that good? All right. I want to give you one, just one, to work on for homework, okay? Make sure it's done, please. Okay, make sure it's done to the best of your ability. Don't come to me with, 3 numbers written down tomorrow and say, I tried it, couldn't get it. Try harder, okay? Show me that you've legitimately tried to do the whole thing, okay? By the way, it's not always 30 degrees. Everybody figured out why I usually use 30 degrees in my examples? It's easy math. Right? Sine 30 is 0.5, cos 30 is 0.866. It's easier to do the math in your head when you use 30 degrees. So it's not always going to be 30 though. Okay. That's it. That's your homework for tonight. Let's get the sum of all these vectors. Remember to do that. We're going to take this one that's at a funny angle, 400 meters, get an x and a y out of it, and then break all of them into x's and y's. Recombine them. And that's it. You got a couple minutes to work on that now. See if you can get it finished up. If not, make sure it's done for tomorrow, please.